In the last section on combinations where we learned about NCR, the focus was on choosing R items from a set of N distinct items. Today the focus is questions where you want to know the total number of possible combinations of any size that you could choose from a given number of items, some of which may be identical. So here, instead of choosing R items, we might even choose more than just R items. We might choose 1, 2, 3, 4, etc. So we'll look at some questions here. If you have a pear, a peach, and an apple in your fridge, how many ways can you choose one or more pieces of fruit to eat? Let's call this item A, B, and C, and let's look at the options here. Find a tree diagram explains this really well. So if we're looking at item A, the question when you look at the pear is, do I eat or not eat it? That's really the simple question you ask when you look at that pear. And then once you've made that decision, you look over at your peach and you say, should I eat it or not eat it? And again, these are parts of our tree diagram. And then lastly, we look at the apple and we ask the same question, do we eat it or not? Okay, so these are a number of options here. So option 1 right here is the gluttony option. This is where you eat all 3 items right away. Okay, right here you would eat the item A, so eat the pear. You would eat the peach, but you would not eat the apple. So that would be one of the options. So what do we have in total here? Well, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 different ways. But you might notice there's one small problem. It does say, how many ways can you choose one or more pieces of fruit to eat? Well, what would the problem be? Well, the problem is if you choose not to eat anything. So you choose not to eat the pear or the peach or the apple. So this right here is really a violation of that question. So we minus 1, which gives us 7 ways. There are 7 ways that you could choose one or more pieces of fruit to eat. Well, we can generalize this. With n distinct items and needing at least one item, we use 2 to the power of n minus 1 as our formula. With n distinct items and including the null set, so null means nothing. Okay, so using that null set, we use 2 to the power of n. So let's go back to this. Does this work? Why does this work? Well, think about it. We have 3 distinct items. So we use 2 to the power of 3. But here we must choose at least one, so we minus 1. Well, 2 to the power of 3 is 2 times 2 times 2, which is 8, minus 1, which is 7. And if you look at the tree diagram, there's a lot of good reason for why it's 2 times 2 times 2. Originally, we start off with a branch that has 2 options here. And then each of those splits off into 2 options. And then each of those splits off into 2 options. So see that every single item we added, the pear, the peach, and the apple, each doubled the number of options of ways that you could choose to eat one or more of the fruit. So it's 2 to the power of 3 minus 1. All right, that's one type of problem here with combinations. Let's look at another. You have 3 pennies, you have 1 nickel, 1 dime, and 2 quarters. How many different sums can be formed? I'm going to start you on the tree diagram, and then I'm going to encourage you to try and draw this out for yourself. Okay, so first of all, you have your pennies. Okay, and there are 3 pennies, and what's unique is that if we're looking at sums of pennies, and you have penny A and penny B, if I give you penny A, you have 1 penny. Or if I take back penny A and only give you penny B, you still only have 1 penny, and your sum is 1 for each. It doesn't matter if you have penny A or penny B. The question really is, how many pennies did I give you? So let's look at that. So you could have been given 3 pennies, or you could have been given 2 pennies, 1 penny, or you could have been given no pennies. Second, we can think the same way for the nickels. I'm going to actually write the values of it. So if you have a nickel, you could have been given 1 nickel, which is worth 5 cents, or you could have been given no nickels, which is 0. So here is my tree diagram. Kudos to you if you managed to make the whole tree diagram fit, because I was struggling by the end here. But compare yours with mine. Again, how many different sums can be formed? So let's just try and understand what this tree diagram is saying here. So the very top spot here, we would add 3 pennies. So 3 cents plus 5 plus 10 plus 50, which would give us 68 cents. Okay, and the next one would be 3 plus 5 plus 10 plus 25, which is 43 cents. Okay, and you can keep going. You can keep going to here, right, where there's 0 plus 0 plus 0 plus 50, which is 50 cents. Here, which we have 25 cents. And lastly, we have 0 cents. What I want you to notice, much like the last tree diagram here we had 2, and then we multiply it by another 2 and by another 2 because it kept getting twice as large. But in this tree diagram, we start with 4, then it doubles in size, and then it doubles again. And then here, because we had 3 quarters, or 2 quarters, it tripled in size. So it was 4 times 2 times 2 times 3. And 4 times 2 times 2 times 3 is equal to 48. So there are 48 ways. Oh, wait. How many different sums can be formed? I know this is a matter of definition and maybe a little bit of an argument, but it would be commonly agreed that this is not a sum because you didn't receive anything. There was nothing in it. So we would take away what's called, again, the null set. Okay, so there are 47 ways. Let's generalize that into a formula. So the formula is P plus 1 times Q plus 1 times R plus 1, and then we just keep going, where P items of one kind, Q of another, R of another kind, when you have some that are alike. So notice that, why would you have 4 options for 3 pennies? Well, the pennies, there are 3 pennies, so you could use all 3, you could use 2, you could use 1, but you could also include none of them. So it actually adds 1 option into the pennies in your number of options for sums. Same thing with the nickels. You only had 1 nickel, but because you could not include a nickel, you have 2 options there. Okay, so what's different from question number 1, problem number 1, is that here we have unique items. You can tell the difference between a pear, a peach, and an apple, but here in problem number 2, there were 3 pennies, and we can't tell the difference between the 3 pennies, nor can we tell the difference between the 2 quarters. Let's move on to another question. Oh no, not another question. We're at the end of our lesson. All right, you're going to sum together a lot of the stuff we've been working through here, okay? So 1, we learned about NPR. This is where order does matter, and you are choosing a certain number of items. There's a specific number of items that we often refer to as R. We could use and choose R. This is when order does not matter, and you are choosing a certain number of items. So here it does not matter, here it does matter, and again we're choosing R items in NCR. Actually, what you might find unique is if we go back up to this question here, that, okay, you have 3 items, a pear, a peach, and an apple. If someone said, how many ways are there to choose one of them? You would say, oh, that's 3, choose 1. But then they could also say, well, how many ways are there to choose 2 of them? Well, that would be 3, choose 2. And how many ways are there to add to choose 3 of them? Well, that'd be 3, choose 3. And what you get here is 3 choose 1 is 3, 3 choose 2 is 3, and 3 choose 3 is 1. And you'll notice that you could either eat only one of them, you could eat 2 of them, or you could eat 3 of them. Those are unique situations. They do not overlap, which is 3 plus 1, which is 7. Which this works when you only have 3 items, but if you had 20 items, you don't want to do 20 choose 1 plus 20 choose 2 plus 20 choose 3. You need to have a better formula like 2 to the power of n minus 1. So that's where we got ourselves today. When each item is distinct and order does not matter, and you are not choosing a certain number of items, so that R thing, it's not there. We're not looking for a specific number. Then we use 2 to the power of n. And then we have to ask ourselves if it's the null case. If the null case is not included, having nothing, we minus 1. Okay, and then our last problem there we looked at was p plus 1, q plus 1, r plus 1. And this is when each item is not distinct and order does not matter. And you are not choosing a certain number of items. So this is p plus 1, q plus 1, r plus 1. When there is a null case, I don't know why there's a space there, but when there is a null case, then we minus 1 at the end. Okay, so you just got to ask yourself that question each time. If the null case is not included, take away the no options.